Hello class, in this video we're going to talk about the concept of vectors. Now vectors may be a word that you never used before in your math class, but after today's video you will be able to use vectors in the math class. So we've been talking about transformations, and really we take the original image, which we're going to call the pre-image, is the original image, and we're going to transform it, and the resulting figure is going to be called the image. The pre-image is the original figure, image is the resulting figure. And as you can see, in this particular example, we have a translation. The pre-image is being moved to a different location, and that's called a translation. Now, if we had these shapes on a grid, we could describe the translation using coordinate notation, which is what we worked on in class the previous day. But instead, what if we don't have a grid? How are we going to be able to describe this transformation if we don't even know what the coordinates of each point are? Well, that's where the concept of vectors comes in. So a vector is actually made up of two pieces, an initial point and an ending point, or the terminal point. The initial point is usually the beginning of the vector, and the terminal point is the end of the vector and is represented by an arrow. It looks very much like array, but in the case of a vector does not have infinite length. It actually stops at the terminal point. So if you notice, the initial point corresponds to a point on the original image, i.e. the pre-image, and the terminal point corresponds to a point on the transformed image, the image. So this top point in the pre-image corresponds to this top point in the image. But if I were to take this same exact vector, and instead of starting it at the initial point of the top left point, what if I were to start it at the bottom left point of the shape? And guess where the terminal point ends up? At the corresponding point on the image. So the initial point corresponds to a point on the pre-image of the vector, and the terminal point of the vector corresponds to a point on the image. And as you can see, if I start the initial point anywhere on the original shape, the terminal point will point to the corresponding point on the transformed image. That's how we know it's a translation, because the initial point is related to the pre-image and the terminal point of the vector is related to the image. Well, how do I describe this vector? Instead of saying, oh, that vector, we need some way of quantifying it, just like we used coordinate notation to quantify this translation. Well, a vector is denoted using this notation: left bracket, horizontal component, right bracket. Now, what is a horizontal component? Well, the horizontal component is the horizontal distance between the initial point and the terminal point. So that can be represented by this horizontal line. The horizontal component is from the horizontal distance from the initial point to the terminal point. And the vertical component, or the VC, is related by the vertical distance from the initial point to the terminal point. And that will describe this particular vector. Now these lengths can be quantified with numbers. The distance between this point and this point would be the horizontal component, and the distance from this point to this point will be the vertical component. Well, what if you have another transformation that moves the pre-image from the original position to a different position? Will the vector be the same? And actually the answer is no. So let's say, for example, we have a different image. Let's say our image is somewhere over here. Actually, move it over here. Okay. I can describe this with a different vector. Remember, the initial point starts at the on the pre-image, and the terminal point of the vector ends on the image. So moving this right here, this vector represents the translation of the pre-image to this position's image. And as you can see, that if I move the vector so that the initial point of the vector is on a different point of the pre-image, it's going to end up at a different point of the image. So then to describe this vector, we would use a different horizontal component and a different vertical component. So in this case, a horizontal component is this length, and the vertical component is this length. So let's talk about how to describe these transformation vectors. And as you can see, for a vector, it has a horizontal component and a vertical component. And when we describe a horizontal and vertical component, we can use a coordinate grid to figure out the length or the distance of the horizontal component and the vertical component. And one thing you should notice that it doesn't matter where on the grid the initial point is and the terminal point is, the horizontal component and the vertical component is always going to be the same. So in this particular case, the horizontal component is going to be the distance between the horizontal distance between the initial point and the terminal point. So in this case, it's going to be a horizontal component of 1, 2, 3, 4, 5, 6, 7, 8. And a vertical component of 1, 2. But as you can see, if I start with the initial point and go to the terminal point, I'm actually going down, which means it's going to be a -2. So no matter where I am on the grid, this particular vector has a horizontal component of +8 and a negative vertical component of -2. Now let's take a look over here. In this case, if I start from the initial point's horizontal component and go to the terminal point's horizontal component, I actually have a negative horizontal component because I'm going to the left. So I'm going to the left, 1, 2, 3, 4. So my horizontal component is -4. And my vertical component, if I start from the vertical point of the initial point and go to the vertical component of the terminal point, I have 1, 2, 3, 4. I'm going down 4. So my answer here is, in both cases, -4. So we have actually here two different vectors, and we have two different ways of a different way of representing them based off the horizontal component, comma, the vertical component. Every vector has what's called direction and length. So this vector has a direction of going to, let's say, south east, and this vertical component has a direction of going southwest. Okay, the length can be found using Pythagorean theorem. So in this case, to find the distance or the length of this vector, I can say, oh, that is the square root of -2 squared plus 8 squared. So in that case, the magnitude or the length of this particular vector is the square root of 68. And over here, the magnitude of this vector, or the distance or the length of this vector, is the square root of -4 squared plus 4 squared. And that is the square root of 32. So since square root of 68 is bigger than square root of 32, then this vector has a greater magnitude than this vector.